So we're in the middle of using basically perturbation theory in order to understand what is the influence of a weak periodic potential on electrons in a lattice. And we got to a point where we wrote down the effect on energy. Okay, which we identified as simply the second order perturbation theory. Okay, two questions. One trivial and one important. The trivial one, why second order and not first order?
Well, the first one is 0 because of symmetry or something like that.
Exactly. The first order, we decided that the integral over u, the potential, we set as 0. If you remember, we said if it's not 0, just subtract or add a constant. Therefore, if you are taking the first order, you get 0, no correction. Okay, the second question, am I allowed to do it?
Why not? I mean, energy, you can define where you're and...
No, I'm not talking on the first order correction. Is this correct? Or let's refine the question, is it always correct?
Probably not. Yes.
You can have a problem if the energies are equal.
Exactly. That's the big problem here. If this goes to 0 or very close to 0, also it's already problematic. Perturbation theory diverges. And you're very well acquainted with it. What it's called? Degeneracy. Exactly. So we have to worry whether these terms appear where this is equal 0, and what do we do in that case? Actually, this is the heart of the matter. This is why free electrons and electrons in the lattice are very different from each other. Let me just draw the spectral lines, the dependence of energy on K. Okay, I'll just draw one parabola. And since I'm drawing one parabola, I'm taking all k's. And where do I have a degeneracy? Here. Okay, you can stop me and say, well, you have a degeneracy everywhere. For each k, this behaves like H. Give me a value of K. You have also the same energy at minus K. Correct?
Yes, it's a parabola. How about it?
It's a parabola. It's always degenerate. Degeneracy of 2. I don't care. Why don't I care? Look what appears here. It's not that the values of energy should be different
It has no difference.
by any amount that I want. It can be different only by amount of the reciprocal vector, right? So actually, I have only very special degeneracy points that have an influence on what's happening here. And these are points that K are different from each other by a reciprocal lattice vector. So call it G0, it's 2G0, 3G0, so on and so forth. Only these cases are dangerous. Only these cases affect my perturbation theory. And why is that? That has to do with the symmetry of the system. The fact that it has this translational symmetry. The fact that into the U's you had only amplitudes of the Fourier transforms that depend on G, not on K. So anywhere which is not these points, and I'm drawing it in one dimension as I did in the previous lecture, but it could be in 2 dimensions, 3 dimensions, that are separated by a distance that is not a reciprocal lattice vector. I don't care about the degeneracy, and I have good old perturbation theory that describes the behavior. The behavior could have an influence, but in a sense it's quantitative, not qualitative. It changes the form of the parabola a bit. Depends on the details of how the potential looks, but it doesn't change the behavior completely. The interesting points are the degeneracy points. There I'll have to do something, and you know exactly what we'll have to do. We'll have to do a degenerate perturbation theory there. And there the behavior completely changes. What do you remember about, I'm trying to give a first a qualitative description in order that we won't drown into the details of the calculation, but see the physics. Because here, as I said, the physics is extremely important. So, what happens in these points? What happens in this simple case, the one-dimensional, 2x2 degeneracy? What happens?
Maybe this is a forbidden area that you get like all the things that you showed last lesson with all the degeneracy.
Yes, but let's go first to the first order or zero order degenerate perturbation theory. What happens there? You have two degenerate energies, and what happens to them?
Split.
They split. That's the only fact I need here. So in case of degeneracy, instead of having two energies that sit on top of each other, we'll have a split here, and here, and here. That's somewhat exaggerated, but okay, we'll do the mathematics shortly. So, after I finish the calculation, and ignoring the boring part of the second perturbation theory, instead of having a continuous parabola, I'll have a series of areas where I have energy levels. But the most important thing is I'll have areas with no energy levels. Okay, so first thing that the most important thing that this lattice potential does changes completely the structure of the energy levels. For a free electron, give me a positive energy, there is a case that works with it. Right? Can always find a case that corresponds to any given energy. Here I have energies for which I have no corresponding K. I can't have the electron in the lattice having that energy. And that is crucial. All understanding of electronic properties of metals and semiconductors comes out from this. Okay, so just terminology. The areas that are around are bands. Can call it the first band, second band, and so on and so forth. And we call this area a gap. Okay. How many electrons, how many states do I have in a band?
One.
Excuse me?
One.
One, I wouldn't call it a band, right? It's a bit.
Maybe infinite. I mean, we all get more.
Certainly not infinite.
2.
2 is the not important part of the band. Actually, you'll have here two end states, n the number of lattice points. Why? Because we divided, if you remember, this point, the end of the first real end, is pi over a minus pi over a and pi over a. And the number of k states, I'm doing it for one dimension, but it's correct for any dimension, is 2 pi over L. And if you remember, L divided by A is the number of points there. So you have here n points, n values of k, and since we have spin, we have 2 electrons per spin. Same here, 2n. Okay. So what? Now I'm presenting a simplistic picture which is not followed necessarily by real 3D lattices, and I'll explain it later on, but an idealized picture. Then it tells you, if I have one external electron per atom in this lattice, where would be the Fermi energy? One external electron, because I don't care about the core electrons, they don't leave the ions, they remain locally. One external electron, one electron in the external shell per atom. Where would be the Fermi energy?
You can still put another electron in the outer shell because of spin.
No, in this, yes, that's true, but where would the Fermi energy be? Okay, how do I calculate or visualize the Fermi energy? I start filling it up, right? I have here 2 n states, but I need only n states. So the Fermi energy will be somewhere in the middle of the band, right? If I have 2 n places in and only n electrons to fill them up, I'll have n empty places, and the Fermi energy will be somewhere in the middle of the band. For this kind of system, we have seen in the previous lectures that the properties of the system are defined around the Fermi energy. The behavior of this system would be very similar to the behavior of a free electron system, because it's not essentially different, right? 1 minute. So I'll drop this bombshell. Now we understand metals. Metals are systems where the Fermi energy is in the middle of the band. Because metals, you have free electrons, and this is the situation. Please.
Just if you can repeat about the Fermi level.
Okay, what is the Fermi level? The highest, the energy of the highest occupied state. Right? The simplest picture of it. So, I have two end states. I have n electrons to fill up. At low temperatures, I'm filling up the lowest energy state. I fill up, and have no more electrons to fill up. I look where is the highest occupied state. That's a Fermi energy. Let's look on the case that I have two electrons. Where the Fermi energy will be?
In the middle of the first band, you say? No, maybe in the top of the first band because there are two metals, like 2n and stuff.
I have two. You wanted to say something?
The first band is completely full this time.
The first band is completely full. The Fermi energy is above it.
So the second band, just the beginning.
Will actually sit in the gap. So this is for 2n. This is for n.
Didn't we say we cannot occupy the gap?
I'm not occupying the gap. I'm occupying the last open state in the lower band, and the first empty one is in the second. Now, a bit of more exact statement about Fermi energy. It's the halfway between the last occupied state and the first unoccupied
So
state.
there's no preference for specific, and there's no reason for him to prefer one state over the other. That's the reason.
No, I'm coming and in this room telling you fill up all the seats in this auditorium, okay? And I tell you that tickets are cheaper if you sit closer or further on or whatever. Let's say closer, no. And all of you want to save money, so all of you sit. You first fill the first row, second row, third row, right? Same here. You fill up all the two end states. You have no reason to go to the next band because there it costs more energy. Okay. So what do we have here? At the Fermi energy, we're radically different than the situation of free electrons. Why? Because for free electrons, the next state is close by to the filled state. Here you have a gap. You can't go immediately to the next band. You try to put in a low energy photon and ask the electron to take the energy. It says, no, thank you, I don't want it. I can't find a state that taking this electron will bring me to it. Same as in hydrogen atom. So, insulators, and that's the big difference between insulators and metals. Why metals are not transparent? Because the Fermi energy sits in the middle of the gap. I want to pass a photon through it. Some electron will just grab the photon, go to a higher state, and no photon, nothing goes through. Why insulators can be transparent, like the glass that you have here? Because a photon can come in and it wants to give its energy to an electron, and it says, sorry, you put me in a gap, I have no states there, no thank you, go through. Same thing about an electric field, which causes conductance. Here, I put in an electric field, I have somewhat more electrons on the left branch than on the right branch. I have more electrons going in one direction than in the other. I have current. Put a small electric field for an insulator. It's not enough to go through the gap. Can't take the energy, doesn't have an influence. It's an insulator. So the bands, a small point which looks almost some small detail in this game, actually describes the world as we know it. You have metals, you have insulators. What are semiconductors? The stuff that we are using for almost all our modern technology.
Materials when you can manipulate these properties.
Let's go even undoped. I'll talk about doped semiconductors in a couple of lectures. But just a pure semiconductor, a silicon lattice, a germanium lattice, a gallium lattice. What is special about them? Well, first of all, they are insulators. They have a gap. So why aren't we calling it an insulator?
The band gap is small enough that when you're in room temperature, you have enough energy to...
Right, exactly. You have there enough energy to go to the next band, and you're already not in a situation that all the electrons can refuse to get additional energy. Some of them just are above and sitting nicely in an empty band and can conduct electricity or do other things. That's why the basic reasons why one of the simplest technological applications of semiconductors is measuring temperature. Why? Because a small change in temperature will change the conductance of this material. Why? Because it depends exponentially on temperature. Go back to Boltzmann. You have more electrons in the conductant band as the temperature goes up, so you measure the current through it. You have a temperature detector. You can choose a semiconductor where certain wavelengths will push you into the conductance band. You have a light detector. So all these technological usages come out of this band. Hopefully we'll get to the point to understand why this band structure enables you to build diodes and transistors, the basic components of all the electronics that we see around it. But again, it depends on the band properties. Okay, let's do the calculation and then I'll talk a bit about two-dimensional, three-dimensional systems and where the simple picture breaks up a bit. So what do we remember about degenerate perturbation theory?
There is a matrix, you diagonalize it.
Right, that's the main thing. What is this matrix?
The interaction, the effect of the perturbations on the states.
So I'll do a very quick refresher, and only for the simple two degenerate states, because that's the things that interest us here the most. Let's say I have two degenerate states, 1 and 2. Okay? I write down a matrix. Where U is the perturbation. Okay, diagonalize it and get the combination of the wave functions for which the degeneracy disappears if I take this combination, and I get the influence on the energy levels. So far, so good. Some of you are looking at me as if I'm speaking some foreign language. Is it okay?
Yes.
can't use the usual term. You're looking at me as if you're speaking Chinese because this won't be applicable here. Okay, so let's do it. Okay, we decided this one notation. These are the two states that are degenerate, right? They have to fulfill two conditions. First, that they are separated by G. Okay, start of the lecture. If they are not separated by G, I don't care that they are degenerate because they don't go into the propagation theory. These points. And the second is if the energies are not equal, they are not degenerate, and again, I don't care about it.
So it could be written as 2G as well. If you want it.
In a moment, I'll rewrite it.
So the 1 and 2 are actually Q and Q minus 2.
So the two degenerate states must be Q and Q minus G. We'll get to the conclusion that Q has to be, at least for, has to be half G in each one in order to get G and minus G. Yes?
Before we said that the states that causes us problems were K minus G1 and K minus G. Where did the G1 go? In our...
Oh, it doesn't matter.
The G1 doesn't matter?
Why doesn't it matter? I sum over all the G's. What is the difference between the two energies? Doesn't matter what is G. Some other G, right? Because I sum up over all the G's. Whatever I put in G1, I can shift it anywhere, right? The only important thing is that the difference is of G. So I can rewrite this condition because it's E0. Right? The square of these have to be equal in order that will be fulfilled. Right? No other way to fulfill it. or if you want. So I write down my matrix. So at the genesy point, our energy is shifted once to plus UG, once to minus UG. So all that I did previously was very general. What is the main effect of the shape of the potential? The size of the gap is defined by its Fourier transform with the reciprocal vector. If it's big, it's an insulator. If it's small, it's a semiconductor. Okay. What happens to the wave functions? Okay, I'm doing now zero order perturbation theory, right? How does the wave function look when I have no perturbation, no underlying lattice structure? How did we call this theory? Nearly free electrons. If I have no potential free electrons. So these guys are simply okay. What are the two wave functions here? I want to be exact. Right? If you need to remember anything about matrix diagonalization, eigenvalue, 2 by 2 matrix, which is equal here and has some value here, gives you whatever appears on the diagonal plus minus u, and the eigenvalues are 1 over square root 2, 1 plus 1, 1 minus. The minus is higher energy. Okay. So I just stick in these guys and I get here something that is proportional . So the states at the highest point in the band or in the lowest point of the band are very close to a standing wave. Okay, not so surprising. Let's ask, how does a wave look for very small k's? It's also a constant. So the only thing I've learned from it is that this is not only true at this point, where you have something that's almost a constant, but also here and so on and so forth. Edges of bands are states which are almost standing waves. Okay. What happens when I have a situation where I have more than one dimension? So I limit myself to simple cubic because of my not stellar drawing abilities, but you want to see fancier structures, Ashcroft or anywhere on the web, you have really lovely pictures of much more complicated lattices. First thing that we have to do there. What is the first thing that I have to do there?
Get solution. Build an Hamiltonian.
First of all, I have to know what is R. And here I'll take a simple cubic. It's correct for any type of lattice, but I'm drawing here on the simple cubic. Okay, so R in this case is okay. Well, it's the beginning of the year, but nevertheless. If you find yourself in a universe with a higher number of dimensions, you can fill it up. Next step is finding the reciprocal lattice. Again, something from the beginning of the semester, probably not all of you remember it, but it's about time to start refreshing. Says let's put in here a scale on the line. Then comes draw the Brillouin zones. Okay, I have drawn it for 1 dimension. Let's do it for 2 dimension. Okay. This square is the first Brillouin zone, equivalent to this this portion of 1 dimensional. I have states out of it, fold it into or treat it as you wish. Do whatever is convenient for you. Now I start filling up electrons. Let's say that I have a filling which is much smaller than 2n. How will this filling look?
It will be like round, like you said.
Yeah, it will be a circle. Fill up all states around K for me, as we did for heat capacity, will depend on the density of electrons. All is good. Do I have to worry here about degeneracies? No, because the smallest difference in G is this size. So anything here, not interesting. The influence of the perturbation theory would be to change a bit the energies here, but nothing catastrophic. So, all good. But what do I know? That around these lines, there I have degeneracies. So these are lines that are gaps. To move from here to here costs me energy. So now I add more electrons. Still will be a circle. Life becomes interesting when I get to the point that I start approaching these gaps. Now I want to add more electrons. If the gap would have been 0, no problem. I move to the out of the band and everything is good. But if I have a gap here, suddenly it makes sense to continue filling up states within the Brillouin zone and not jumping out. So suddenly I get instead of a very simple, trivial type of structure, a sphere, I get something here with bumps and if I have not something more complicated than a single cubic lattice, I can get real weird shapes here. I continue and continue and continue till I get to the point that I breach. And I still don't want to get out of the system. I fill up and fill up and fill up. Till at some point I'll breach and move to the next. Now here is something quite nice. In all this game I can move, add G's, subtract G's as I wish. That's my way of presenting stuff. Look at the green structure. I can take it and move all the parts by adding G's and get a circle. Right? Geometry, nothing beyond. But it has a lot of physics in it. Because it tells you the same as the situation here where I have a few electrons in the sample and it looks as a simple 3-electron system. I can think of an almost filled band as a free whole system. Because these regions are regions where I didn't feel electrons. Maybe you remember, probably not. Somewhere a month ago I told you when they went and measured the Hall effect, they sometimes measured positive charge carriers. We said, how can it be? Here's the answer. Well, the band was almost full in these metals, and the behavior was as if I have a small number of positive carriers. So, when I'm much below filling of a band, behaves as if it's free electrons. Where I'm close to full filling, I am similar to the case where I have free holes. So we again, all this gap business explained another phenomena. How come we see positive charge carriers in metals? The answer is we don't see positive charge carrying particles in a metal. There's a lot of negative charge carrying electrons, but the behavior of the system is similar to just a few positive carrying charge. In the middle, we can get properties that are very different than free electrons. Because there you can see it doesn't remind us of a circle, it has a complicated Fermi surface, a lot of magnetic and other properties and conductance properties come out from this behavior. Fortunately, we don't have time to delve into all these details, but the important thing to know is one can experimentally take any system, measure the response, let's say, to a magnetic field and learn something of the structure. You can reconstruct the Fermi edge structure out of all kinds of experiments. So this is not just a theoretical concept. This is something that can actually be measured, and from the measurements you can reconstruct the materials. And people who are doing material science, meaning trying to build materials that have certain properties, magnetic, conductance, whatever that interests them, response to temperature, go and play these games of creating the material, measuring, reconstructing, and then from theoretical considerations saying how should I change the lattice or how should I change the atoms in this structure in order to change the properties. You can easily see that if you replace in some complicated lattice an atom with a certain number of electrons in the external shell with a different number of electrons, this will shrink or expand. You'll get different properties. Changing the lattice structure will change everything, of course. Okay, the same for 3 dimensions, the same idea. So everything is dependent on the size of the gap here. And it depends on the potential, depends on the lattice. All of that are details that fortunately we don't have time here to really get into all these details. Okay, I told you that in the previous lecture Okay, this is one way from free electrons. I want now to go into this problem from the opposite direction, from tight binding. And first of all, in a very simple way, I'll prove you that the main result, i.e. having a gap, remains. Actually, it's even more natural from the other direction. Well, it makes sense because we see that the stronger the potential, the larger the gaps. And the case of tight binding is a case where basically we're starting with a very strong potential of atoms. Okay, so first of all, in a very pictorial way, I'll try to convince you in the result. Okay, what's tight binding? We have a series of atoms sitting at a distance. I'm drawing it one-dimensional. Okay, what did I draw here? Basically, Coulomb potential from the nucleus of this atom and states, if you want to imagine, states of the hydrogen atom. Good. That will be, let's say, so on and so forth. Now, if these atoms sit alone, lovely, I have a set of n electrons which have, n atoms which have some spectra and all is good. If they start sitting close to each other, they have a case, they can, and there's a perturbation. What kind of perturbation exists between them? When this atom sits alone, doesn't feel any other potential. But here it has also some potential from its neighbors. So I have to put it in. Okay, you can say, but that effect is quite small. It falls off exponentially. What do I care about it? No, I care about it for the same reasons that I cared about the situation in the previous case. All these states are degenerate. So a small perturbation, nevertheless, can have an effect. And what is this effect? Exactly as we have learned from perturbation theory, It just moves part of the states up, part of the states down. Meaning that instead of n degenerate states that I had here, so on and so forth. So I get basically very similar physics to the one I got from free electrons. The difference here is that here in nearly free electrons, the gap was the perturbation. Here the band is actually the perturbation. But it makes complete sense, because there I started from free electrons with no gaps, and saw that because of the symmetry of the lattice I get gaps. Here I see the picture, the reverse picture. I start from degenerate states, all of them sitting at the same energy, and they're widened. And large gaps which become smaller. Now you can see from here that the fact that, for example, I have higher degeneracy in higher states, and the fact that I can have shells and subshells that depend on N, L, and M, can break up these bands in a different way, and that's the beginning of understanding why different metals can have a bit different behavior, and our simple rule of 2n filling a band is not necessarily completely correct. But our main result, which is Fermi energy in the gap insulator, Fermi energy in the band, it's metal remains correct. Okay, another name that I didn't mention previously, but it's, let's say I have a Fermi energy in the middle of this band. Just as convention, a filled up band is known as a valence band, and a partially filled band is known as a conductance band. So let's say for an insulator where the Fermi energy is in the gap, the valence band is completely filled, and that's always correct. But there the conduction band is empty. Okay, so I hope the physics is clear. Let's do the mathematics. So tight binding. What is the unperturbed Hamiltonian?
The free electron with the Coulomb potential.
No. That's free electrons.
The del times the del squared and then the
No.
the Coulomb potential.
No, I want it even simpler. All the logic here is I start from an atom and put them in an array, right? In a lattice. So my basic building block is the Hamiltonian of an atom. I assume that I know to solve an atom or a well or whatever I'm putting there. Okay, nowadays they are creating such wells that are not necessarily atomic out of interference of lasers. Because you have an electric field, you can create areas that are strong electric fields, low electric fields, so it's not exactly the Coulomb structure, but again, it's a place that you can capture atoms. It's a potential well, and it has some form, not necessarily that of an atom, but who cares? All I need from it is to understand, in this case, I know to solve the levels of the atom or the well or whatever. That's my game. H in the vicinity of some atom and is the Hamiltonian of the atom plus whatever influence of all the other atoms extract on the vicinity of an atom. And what does it depend? It depends on the exact lattice potential and the structure of the particular structure. Okay. The wave function of the whole system or the zero order wave function of the whole system Okay? What does it mean? It's basically, if I have no influence of one atom on the other, I'm completely free to choose the weight of the wave function on each of these atoms. What is the only condition that I have to fulfill?
No places in the band, maybe? No, in the
I
galaxy.
don't have yet a band because delta U is equal 0. They are degenerate.
Probability equals 1 or something.
The produce.
The periodicity is already taken into account here.
Maybe not all the probability goes over 1 or something like that. Normalization.
Almost all I have to worry about is that normalization. Do I have something else to determine the properties? No. Each combination of ARs that fulfill this condition is a good solution to the system. So I can have all of them sitting on one atom, all the weight of the wave function, or I can have it divided completely equally between all the atoms, or any other combination. Basically, why? Because these atoms are not aware each of the other, and there's no gain of sitting on one atom or sitting on all of them or sitting on part of them. All of them are good. It's a very degenerate state. What is the degeneracy of this state? N. Or 2n if you're
Spins.
taking spin into account. What else do I have to fulfill? Only Bloch's Bloch, which tells me and that actually decides AR. This is our good friend. So now you can stop me and say, excuse me, a minute ago you explained us that AR can take any value. Here you claim AR has to take this phase structure. Why is this discrepancy? Once I put in delta U, I'll be forced to do Bloch's theorem. Again, as for nearly free electrons, that we saw that once I decide on the structure of the lattice before putting in an actual potential, I already get these blocks, these Brillouin zones. Here, stating that I'm in a lattice already forces me something on AR. Okay, so we have to go and do perturbation theory here. It will take us about half an hour or so I don't want to start now. So we know what is a model, we know what are constraints on the wave functions and the energies. We know what we expect as a result. We have to just do the mathematics and see that indeed that's what we get. Okay, so I'll stop here and we'll continue tomorrow at 7 o'clock in the evening here.
Thank you very much.